Okay, as promised, in this video, we're going to actually look at some differentiation rules for function types and combinations of those things. So to start, we're going to start off with constant functions, and we'll prove a derivative rule for those. Then we'll move on to power functions, and we'll do everything but prove the derivative rule. We'll give lots of good evidence for it, and I'll convince you of the derivative rule for power functions. Then we'll look at some kind of general things where we're multiplying functions by coefficients or adding and subtracting functions together. And again, what we care about is differentiating all these different combinations. So let's jump into it. Our main goal here is that we want to use this limit definition of the derivative to get a shortcut. Using this limit definition every single time is something that we can do so far, but it's at the very least difficult. It's going to take a long time for us, and we've already run into some cases where it might be a little tricky to apply this limit definition to certain types of functions. So we want to be able to come up with some other shortcuts so we don't have to do this kind of limit work. As we go throughout the semester, we're going to be adding a bunch of derivative rules for function families as we come up with them. So we'll look at exponential functions and logarithmic functions and trigonometric functions and inverse functions and all that kind of stuff. Eventually, we'll have a long list of just known derivative rules for general families of functions. What we're going to do for now, though, is start really small with constant functions. So a constant function is just this nice good old-fashioned y equals 7 or something like that. Intuitively, we can probably figure out what's going on here by just drawing a picture of a graph of a constant function. Here's my constant function y equals 7. It's just a horizontal line. And it should be pretty easy to see that the slope of this line is 0 no matter where we are on the line. So you can put a point anywhere on this function, and it should be pretty obvious that the instantaneous slope of this is 0. So the derivative of a constant is 0. Let's prove it, though, using that limit definition. What we have here is we're going to let k be some real number, and that's our function. What we'll notice is that if f of x equals k, then f of x plus h is also k, because there is no input x to change. So this is our f of x plus h minus f of x. But notice k minus k is just 0. 0 divided by anything is 0. Some people might look at this and say, wait a second, isn't this indeterminate? 0 over 0. Notice, though, when we're looking at limits, h is approaching 0, but it's never actually equal to 0. So we have 0 divided by a non-zero number. Before we apply the limit, we can just say this is the limit of 0. 0 is a constant. We know that the limits of constants are just themselves, so we get 0. So, like we said, the derivative of this function is 0. We could do a whole bunch of examples of these, but I honestly don't think it's worth our time. Let's move on to something like this. Power functions. So for this one, we're not actually going to prove it, but we will just work on some of these. We'll try a couple. We'll see what kinds of processes we have, things like that. So what I'm going to say is let's start off with f of x equal to x squared. That means that our derivative is going to be the limit as h goes to 0. And now I'm going to apply that definition of my derivative. This is x plus h squared minus x squared all over h. Again, that's f of x plus h minus, f of x. There we go. Now what we need to do is just multiply this out. X plus h squared is something that we can do. That's x squared plus 2xh plus h squared minus x squared all over h. And again, that's just coming from x plus h times x plus h. Multiply all that stuff out, and you get x squared plus xh plus xh plus h squared using the distributive property. So that's what we've got right here. All right, now we can notice there's an x squared minus x squared. We can combine some like terms. This becomes a limit as h goes to 0 of 2xh plus h squared over h. We'll also notice there's a common factor of h on everything. And so we can say this is a limit as h goes to 0 of 2x plus h over 1. Or maybe I'll just say 2x plus h. And now finally, this is a really easy limit, right? We can just evaluate this at h equals 0. And so we have 2x. So what we've just found is the derivative of x squared is 2x. Great. Let's do this again for x cubed. So we'll set things up in the same way. We'll say f of x is x cubed. That means f prime of x is the limit as h goes to 0 of x plus h cubed minus x cubed all over h. Pause the video and see if you can finish things out. If you need to look back at this example to just see what we did, you're going to notice that it goes really, really similarly. So go ahead, pause the video, finish this limit out, and when we come back, we'll talk about it. All right, so hopefully this is what we've found. You'll notice that doing this multiplication of x plus h cubed is a little annoying now, right? We have to multiply that 3 times. So here's the work over here on the left. Make sure that that's what you got. That's probably where things are going to fall apart for us, really. It's really easy to just misplace a term or miswrite an exponent or something like that. Anyways, once we have that f of x plus h part figured out, we again notice that there's some like terms that we can subtract, and then we again find a common factor of h that we can cancel out, and now we've just got a nice little polynomial thing where we can evaluate at h equals 0, and since we have this 3x squared term in the front without any h's in there, that's what we're left with. So we've got that the derivative of x cubed is 3x squared. So here's what we've got so far. And the question is, what is this? The general power function x to the n. Now this is where we can come up with a proof if you'd like, but the proof is going to rely on knowing the binomial theorem, which I'm not going to prove that thing in this class or in this series of videos, and so I'll use the binomial theorem, but what I would rather do is give a visual of what that is. So here's our general setup for the proof of that general power function. We have this x plus h to the n minus x to the n, and like we found with the cubic function, the hard part is this x plus h to the n. So what I'm going to do is draw this little triangle of numbers. Maybe you've seen this before. This is called Pascal's triangle, and at first glance it's just a cute little pattern with some numbers in here. So the general idea for Pascal's triangle is we try and figure out what the next row of numbers is for the triangle. You'll notice that each row is one more value than the last. So in the first row we have one number, in the second row we have 2 of them, in the third one we have 3 of them, fourth we have 4 of them, etc., etc., etc. And then you'll also notice some patterns. But what we're going to focus on is these kinds of patterns. We're going to say that each row starts off with a 1. You could say it's really like a 0 plus 1. And then every number after that is the sum of the 2 numbers above it. So this is going to be 1 plus 4, that's 5. This next one is 4 plus 6, that's 10. 6 plus 4, that's 10. 4 plus 1, that's 5. And then we have like a 1 plus, I guess, 0 because there's nothing over here. So call it 1. All right, cute. This is a nice little pattern of numbers. How does this help us? What I'm going to say is that we should recognize these coefficients from things that we've done already. If we go back to our examples with the x squared and the x cubed, let's look for those coefficients. 1, 2, 1 and 1, 3, 3, 1. I see a 1, 3, 3, 1 right here. And here is our 1, 2, 1. I didn't write it, but there, 1, 2, and 1 here. I guess I can write x squared plus 2xh plus h squared. And so there's our 1, 2, and 1. So Pascal's triangle gives us the coefficients of these binomials, these 2-term polynomials, multiplied to powers. Then we can notice there's another nice little pattern that you might have already noticed. The exponents on one variable count down, and the exponents on the other variable count up. So you could think of this as x cubed times h to the 0, and then we go down an exponent on x and up an exponent on h, and we just keep trading those things off. So Pascal's triangle really gives us a great way of finding x plus h to some power. So for instance, x plus h to the 5 is easy enough for me to do. I know I'm going to start with x to the 5, and then my next coefficient is 5. So I have 5x to the 4 h plus 10 x cubed h squared plus 10 x squared h cubed plus 5 x h to the 4 plus h to the 5. That's giving me my f of x plus h formula. Then what you will notice is that in our examples, we had the same sequence of events happening. That first term was the exact same thing as the function, right? Which makes sense. That's just the x part multiplied by itself 3 times. So we were able to subtract those. All of the other terms had h's in them, and we were dividing by h, so we can reduce the power of h by 1. And one of those terms only had a single h on it, so when we canceled out h's, we were left without any h's. All the other ones had exponents of h higher than 1, like 2 and 3 here. And so when we divide by h, we're still left over with some h's. That all went to 0. So what is this 3x squared term? This 3x squared term is right here. In this Pascal's triangle, in the binomial theorem, this is really 3x squared h, but remember, the h goes away. This first term canceled out. All these other ones had extra h's on them. And so we can figure out what's going to happen here really easily. Here's how it looks written out. This is our f of x plus h thing. I'm leaving out all those middle coefficients, but you'll notice that we always have n here as that leading coefficient on the second term, right? These are all just whatever the exponent was. And so what we can do is notice x to the n minus x to the n. And now we've got nx to the n minus 1 with an h here. And there's h's on everything. So we can cancel out h's. And a whole bunch of terms are going to be left with h's, but this one won't be. And so that's what our limit is going to be. Now, if you don't believe me, just go back and recreate this. Try it with x to the 4 and x to the 5. And you've got all the coefficients that you need here. So it shouldn't be too hard to get those x plus h's to the 4 or x plus h's to the 5. And you'll notice the same pattern of events. Now, this isn't a proof because we would have to prove the binomial theorem. That's the thing that tells us all of those coefficients and all of these terms in the middle. But hopefully you can see the structure of all of this. All right, so here's the derivative of a power function. If you've got some function x to the n for some positive integer n, then the derivative, we just take this exponent out front and subtract 1. That's it. So we can do some examples if you'd like. If we want to, maybe I'll just use the derivative notation. If we wanted to do like x to the 10, that's easy. That's going to be 10x to the 9. No problems. So we don't have to go through that limit definition work this whole time. There's a more general power function. Notice that in this first one, we said this is for some positive integer n, and now we're saying for any real number k. The proof of this is something that we will need to do later on in this class. We can't really prove this one yet easily until we learn about things like implicit differentiation and the derivative of logarithmic functions and stuff like that, or at least that's a nice way of proving it. So maybe when we get there, I'll toss the proof of this in a video so we can see it. But essentially what we're going to say is even if we don't have integer exponents, it still works out the same way. So what that means is that if you have something like the derivative of a square root function, that's really the derivative of x to the half, you can do the same thing. You can go ahead, bring this exponent out front and subtract 1. So this is really a half x to the half minus 1, that's negative half. Or you could write this as 1 over 2 square root x. We've probably seen this already because we can do this derivative with the limit definition. But now we can just use this more general power function rule. Easy enough? Good. Okay, what about operations between functions? Like, for instance, what about coefficients on functions? What if we don't just have x to the 10? What if we have 5x to the 10? Well, this rule says that as long as you have a function that's differentiable at this value x that you're looking at, and as long as k is just a real number, then this coefficient just kind of sticks around and gets multiplied on the derivative. Another way of saying this is that the derivative of k f of x is equal to k times the derivative of f of x. We can like factor that coefficient out. Here's the proof of it. It's really not hard. It exactly is factoring the coefficient out of the limit definition. So we've got k times f of x. So here's k times f of x plus h and k times f of x. But notice now that's a common factor in the numerator. So let's bring it out front. There it is. Hey, look, we have a product of things here. The limit of a product is the product of the limits. So we look at this limit of k and the limit of the rest of this stuff? Well, this is pretty clearly f prime of x. That's just the definition of it. And we know that if k is constant, then that's literally just k. So we have k times the derivative of f of x, or kf prime, same thing. What this means is that for coefficients, you can just leave them out front and worry about the function itself. We'll take a look at some examples of that later on. Sums and differences, this is another really nice one. If you're adding functions together or subtracting them, you can just look at things piece by piece. You could almost say here that this derivative, it's kind of like it gets distributed, right? You can like apply the derivative to f and the derivative to g. Now, it's not multiplication here, so it's not exactly the same thing as the distributive property that we know, but it's got the same structure, right? If you have sums and differences, you can apply this derivative on each term. And here's the proof of it. It's not too bad. I'm going to call this function s for sum, and I'm just going to do the sum version. You can imagine how the difference version goes. It's exactly the same. So we've got this sum of f of x, or sorry, of x plus h minus the sum of x. But this is really f of x plus h plus g of x plus h minus f of x plus g of x, because again, that's how we're defining this s function. And so then after this, we just rearrange stuff. I'm going to take this minus f of x and put it over with the f of x plus h. I'm going to take this minus g of x and put it over with the g of x plus h, split these fractions up, apply the limit across the sum because we know that limits do that, and suddenly we get the limit definition of each of these derivatives, f prime of x plus g prime of x. What you'll notice is that if you look at the difference function, it goes exactly the same way. So there's really no big issues. So the derivative of the sum or a difference of these functions is really the derivative of each piece. Okay, that was kind of fast for those. But just as a general summary, what we have now are a couple of different ways of attacking function types. We have constant functions, we have power functions, and we have combinations of those with coefficients and sums and differences. That means for a function that we want to differentiate like this, 7x squared plus 4 square root of x minus 8 over x squared. This looks complicated, but as long as we can write this as coefficients on power functions that are added or subtracted together, then we'll be able to take a look at breaking this into pieces. After some work, you'll be able to write this as 7 times the derivative of x squared plus 4 times the derivative of x to the half minus 8 times the derivative of x to the negative 2. And on each of these derivative things, we can apply that power rule. Bring the exponent out front, subtract 1 from the exponent, and we're done. So that's what we've got. We have a really nice path through these like polynomial functions and other power functions, even things like reciprocal power functions or radical functions, where we can write them with some real number exponents. That works out really nicely for us. We'll take a look at more examples in a little bit, but that's what we've got so far. Hopefully this is looking exciting because this means we don't have to spend near as much time with that limit definition of the derivative. We're going to move on and take a look at the exponential function e to the x by itself in its own video, so we'll take a look at that one next, and then we've got some examples after that.